Hello, everybody. My name is Thias Guns. I'm a professor at the AI lab at KU Leuven, as well as the data analytics lab at VUB. Both are in Belgium. And I really work at the intersection of constraint programming and machine learning. And so I publish in both communities and so forth. Now, I originally was only going to talk about my work at the integration of the two, but as one of the speakers had to cancel, I discussed with Christian. And I believe that if you're working at the intersection, you really have to learn the details and respect the typical problems of each of the communities. And so given that Pierre already gave an introduction to constraint programming on Monday, I propose to also give a bit of an introduction on the principles of data science today. So the outline of the two sessions I will be giving is this. So this morning, I'm going to talk about an hour about the principles of data science. And after that, about a first work at this intersection, mainly learning from the user. And then there's a practical session. So last night, you all received an email with links to the notebooks. They're actually on GitHub. And so you will be able to build your own neural network and do some constraint optimization over that. In the afternoon session, then I will talk about two other forms of integration, namely learning from vision problems and learning from the environment, both for the purpose of learning part of the input of a constraint program. And then there's a second part of the practical on a second notebook. All right, so let's get into this. So for this part about the principles of data science, I was heavily inspired by this book called Data Science for Business. When something is called for business, it's not always attractive to computer science, but what I really like about this book is that it focuses on the key principles and on the high level ideas rather than on the algorithmic details. And I'm also using lots of slides of other people in my presentation. So what exactly is data science? I used to call it the new hype, but nowadays you have to call it the previous new hype. There's actually many different types of words, big data, machine learning, deep learning, prescriptive analytics, AI, data science, and so forth. And I will talk specifically about data science. They're actually all very connected. The thing is that there is not a single definition of what is and is not data science. But what is clear is that there are a number of components, and anything that fits these components can be called and is called data science. So the first component is, of course, that it has to be data driven. And the more data, the better. And that's the whole big data point of view. A second important component is that almost everything in data science is highly interdisciplinary. So it's at the intersection of math, statistics, computer science, and so forth. And I would say the general goal of almost all approaches to and problems in data science is to extract knowledge from observed data. So you've observed data and you want to extract knowledge from that. So I'll shortly give three things that I think are clearly high success stories of data science approaches. The first one is called automatic image captioning. And so what you see here is an image, and this image is given as input to, in this case, a neural approach, and the output is the text written underneath. Okay, so there is no person involved here. This network is given an image and it produces the text below. And of course, it was trained to give summaries of the main elements present in that image. And so man in black shirt is playing guitar. And in order to do this, it got millions and millions and millions of pairs of images with a short sentence, and it learned to automatically construct new sentences based on new images, which I think is very impressive. But of course, if you pay detail, then you will see, I don't know if you see my pointer, but you will see that there are some mistakes being made. So the top right image says 2 young girls are playing with Lego toy. And so it accurately identified Lego toys, but the other person to me is clearly not a young girl, is probably the mother. But even without that, it's a very impressive result. Another success story, much closer to most of us, I would say, is recommender systems. In this case, I'm showing an image of Netflix, and actually every row that you see here is populated by automatic recommendations. So Netflix analyzes the viewing behavior of all of its users, and based on what the kind of things that you have viewed and what other people have viewed, it will recommend what you are likely interested in. So it's actually able to learn human preferences, to learn your interests, even though it doesn't know that one movie is an action movie and another movie is a romantic movie. Even without knowing that, it can learn those preferences. And then the third success story, a bit of an older one, let's say, but still important, is that of spam detection. And so we've been having spam detection in our emails since a very long time, of course. But I would say that this was one of the first, or a clearly first, very widespread, everyday used application of machine learning and data science by almost everybody. All right, so it says here common data mining tasks, but you can use it interchangeably with data science. So what are the common tasks in data science? The most typical task is that of classification or class probability estimation, which answers the question of how likely is a consumer, for example, to respond to our campaign. And another main problem is that of regression, namely to estimate not a class and not the probability that you belong to a class, but to estimate a certain value. For example, price, cost, how much will somebody use a service, and so forth. And then there's a number of other tasks, similarity matching, clustering, and so forth. And we can make a differentiation in those tasks between supervised methods and unsupervised methods. And a method is called supervised if in the data, and so the historical instances, the training data that you're given, if you know what the true value to estimate is. For example, if you're giving an image of a handwritten letter, then you know that this should be a 5. So if there's this label, then it's called supervised learning. And if there is no label available, then it's called unsupervised methods. So for example, clustering, given images of cats and dogs, you can actually ask a method to cluster these images without telling it upfront that this is about cats and dogs. Clustering is also used, for example, in marketing to automatically cluster customers based on their kind of consumer behavior. All right, so that's what I just said. Spam or not is an example of a label. A bit of terminology that most of you are probably aware of, but I just want to repeat it to have everybody on the same page. So data in many cases in data science consists of tabular data. And in that case, we speak of the data is in tabular data, so it's a table. Each of the columns is called an attribute. One of the columns, in case of the labeled the supervised learning, is the target attribute or the label. And then each row is what we call an example or a training instance. And so given, for example, this training instance, so a value for each of the attributes, you should predict what the label of this instance is. I've already said this in the beginning. So most books on data science and machine learning have an algorithmic or statistical focus. And I've used this one because it looks beyond that. And so I like this quote, which says, in 10 years, from the book, an introduction, in 10 years' time, technologies will likely have changed such that today's choices seem quaint. And at the pace that machine learning is advancing, this is very true. And nowadays we use PyTorch, but in the beginning it was all TensorFlow, and in fewer times it can change completely again. So it's not so much the implementation or the type of technology as it is the principles that matter. Because before that, it was mostly SVMs. All right, so on to the principles. The first principle is that data science is a process, all right? So what does this mean? Well, when you do data science, you always have to first collect the data, then you need a suitable way to store it, to retrieve it, and only then can you analyze it. This is especially true in cases that involve real-time data. So in earlier days, so this is a bit of a chronological overview. So a collection was usually manual in 1950s and so forth, but as more and more companies and systems digitized, this became more automated. Also in terms of storage, there has been a whole evolution from ad hoc databases of files to relational databases, object relational databases and so forth. And the same for the retrieval and analysis, where nowadays we can do lots of advanced analysis, and this is typically being pushed back all the way up to the collection and the way that this is stored. For example, in big data, in Hadoop pipelines, you're actually doing the analysis on specialized representations, federated representations of the data. But I'm not going to talk about that today. It's just a bit to let you know that it's always a process, and there's a formalization of this process already since a long time called the CRISP-DM process, which says that whenever you start a new data science process, you have to start by understanding the business problems. And after you understand what the business needs are, you can start looking at the data and what the data looks like. It will undoubtedly be noisy, missing values, wrong values, and so forth. So there's a data preparation step in which you need to modify this data so that it can be fed into machine learning systems. And that means, in most cases, it means making it in a tabular form. Once it's ready to be used in tabular form, for example, there's different ways of modeling the machine learning problem, different types of techniques to use, and so forth and so forth. And whether they work or not should be evaluated. And this evaluation is typically at the machine learning level, using accuracy, using raw curves, mean square error, and so forth. But it's important to map these results back into the business understanding. And for example, if you're doing this in the context of vehicle routing, you shouldn't just evaluate how well you match the distributions of the vehicle instances that you've seen, but as Daniel was arguing, you should map it back and see if you can now actually solve, for example, the X instances much better. Okay, and that means that if it takes too much time to generate the features, well, you're actually not solving the problem. And so you should reconsider and find another type of data preparation that is less time computing so that you can solve the business problem. An example, as for example, let's take the spam email again. So what is the business problem here? Well, we get a lot of emails and many of them are spam. Why is this a problem? Well, it's a problem because it reduces our productivity, because we have to click each of these messages, and it would save us time and remove the clutter if this would automatically be removed. All right, so what does the data look like? Well, the data is just plain text. Actually, not just plain text, you also have a header. And given this message, you have to predict whether this is spam or not. And so this is actually a text categorization problem, which is useful in general. And what we basically want, if you really go to the essence, is you want to learn a function that maps this message to either the value 0, namely it is not spam, or 1, it is spam. And this is, of course, a typical binary classification problem. All right, so we have a data understanding. Then we can look at the data preparation. And so this means, let's say we start from the raw text, or maybe we separate header text from body text. And then as for modeling, the old school simplest approach would be to create a rule-based system, such as if the title contains UF1, then it's spam. All right, of course, this is silly, yeah, but let's just walk through the process. And so then you're going to evaluate whether this rule is a sufficiently good or not. And this evaluation in machine learning is typically done based on a data set that you did not use for training, actually always, and it's the test set. And you look at how many messages were predicted as spam and how many of these test sets were predicted as legitimate and which were actually spam or were legitimate. And then you see what your true positives are, what your true negatives are, but you also see the false positives and the false negatives, okay? And so this means that in this case, for example, 200 of the emails that actually were spam were predicted as being legitimate, so shown to the user, and 30 actual emails would be removed because of being spam. So whether this is good enough or not has to be evaluated from a business context. Okay, so the question is, how can we find better rules? And actually eliciting this knowledge or coming up with different types of titles and so forth may be difficult. And also, how do we define good? And what actually is a spam message? It could be that that emails about Viagra are spam to me, but maybe not spam to some other people. There must be a market, otherwise these emails would have stopped long ago. So what we actually need is not just a system that decides the same thing for everybody, but a system that adapts, that learns, also based on the feedback from the user. All right, so let's use a classifier to do this. So the data understanding, we have to get messages, both spam messages, the negatives, and legitimate messages, the positives. I swapped the labels here. As data preparation, we can go to a bag of words representation, meaning that every message is reduced to the top 100 most frequent words, for example. We can then train a classifier such as naive Bayes, evaluate an unseen emails, and then when we deploy it, we will predict this for new emails, but we also give the customer, the client, I mean us, right, the email reader, the choice to flag additional emails as spam or to correct that a message was not spam in the spam folder. All right, so that's really the first principle, is that it always is a process and you always need multiple iterations to make sure that you're solving not just a machine learning problem, but that you're solving the actual problem domain problem. The second principle then is that machine learning is optimization. And that's good news for us constraint optimizers. And more specifically, it optimizes loss functions. So all of machine learning is continuous, actually, mostly optimization. Let's have a look at the formalization of that. And so we typically have a space of possible instances. And this is, for example, the table and what values each of the attributes can take. There is an unknown target function f that we're trying to learn, which takes an instance from this space of possible instances as input and should predict the output. For example, a one-hot encoding of a number of words, and it should say whether this message is spam or not. How does learning happen? How do you search for this function? Well, there's a hypothesis space. There is a definition of what valid functions are that map X to Y. In case of a neural network, this is defined by the weights of the network. And then, of course, a set of examples where we are given both the instance X and its label, so the true outcome of applying the unknown target function f of X. We can measure how good we do with that loss function. So this applies, this should have been, so H, so H is the model that we're going to learn. It applies this to a set of examples and it gives you a real valued number, typically between 0 and 1, for example, accuracy. And so the goal is to find a model, to find an instance of this function that minimizes the loss. Okay, yes, I've said that. So let's have a look at the most simplest case, which is linear regression. So in case of linear regression, we're given data points. So it's an n-dimensional vector of real valued values. And the label is also a single real valued vector for every, a single real value for every vector, as for every training instance. And the function that we're looking at are linear decision functions, meaning that you're multiplying a certain weight with every vector of your feature vector, and this is the output of the function. And so what is the space of possible functions? Well, it's the space of all possible values given to W. Now we of course have to find the right W. So we have to define what a good W is. We have to define the loss function. Yeah. Well, what we can do is for every new test point X, and we will estimate the label. We will make the prediction by multiplying the learned weights by that feature vector. And then we get a certain prediction. For example, the prediction here on the line. We can measure how much off we are. Our prediction is off on the actual label. Here, that's this, by, for example, taking the square of this error. And now the question is, okay, if this is how we measure how well the predictions are, can we optimize this squared error on a training set? And the answer is yes. So this loss function is a sum of squared errors. It's convex. So we can use convex optimization to solve it. And then this is actually the least squares regression problem. Good. Let's have a look at somewhat more complex functions, deep learning. In this case, so I'm showing an image of a network for recognizing handwritten digits. And so the function is a bit more complex. The function consists of a 5x5 convolution first, then some max pooling, another convolution, some max pooling, and then a fully connected network. Right? So this is a certain architecture, but what's important is that on every line that you see, there is a weight. Just as in linear function, there was a weight for every coefficient. Here, there's a weight for every line that you see, and it's a matter of, and it's once this architecture is defined, it's just a matter of defining the proper weights to produce the output. And the possible outputs is it's a digit 0, it's a digit 1, it's a digit 2, and so forth up to 9. So this is obviously a more complex function. How can we do this? Well, we cannot use convex optimization to find the global optimum as we could for least squares regression, but we can use other types of optimization approaches, such as very popular stochastic gradient descent. So let me give you a bit of a, so what's funny is that from an optimization point of view, this is really simple, right? Stochastic gradient descent is a very primitive form of optimization, but because we're training such complex models, this actually makes sense to do it this way. So what does it typically look like? And actually in the practical later, you will see that this code is explicit and that you can change parts of it if you want very easily, and we will use the PyTorch framework. So what does stochastic gradient descent look like? Well, you're assumed given a training set, so given instances X and labels Y, as well as a learning rate. You first initialize the neural network weights, here depicted by theta. And then we will go a number of times over the data. And every time we go over the data, it's called an epoch. In each epoch, we sample a subset of the instances. And for example, we sample 64 of the instances of the training data. That's what's happening on line 4. We compute the predictions. In neural network talk, this is called the forward pass. And so you give the input to the network, you propagate it to the network, and you observe at the end of the network what the outcome is, what the prediction is. Then you have to compute the loss function, so the difference between the predicted values and actual values for some proper loss. And from that, if it's differentiable, you can compute the gradient of that loss function with respect to all of the parameters in the neural network. And then updating these weights using this gradient multiplied by the learning rate, so the step size, so to say. And this is done through backpropagation, and that's what we call the backward pass. So you compute the loss at the end of the network, then you compute the gradient, you update all of the weights immediately before that, and then you go one layer below, and this, by applying the chain rule, you can keep updating all of the weights appropriately. And you just repeat that, and then your weights at some point well, you will get a classifier. Now, it's amazing how this simple training mechanism, this single type of optimization, what it all allows you to do. So for example, the example that I showed with the image captioning, no, this is actually a slightly different example. So in this example, you're given an image as input, as well as a question, namely, is this person dancing? And then you have a range of possible outputs, because in this visual question answering setting, I could also ask, for example, how many people are on this image? And then it doesn't have to answer yes or no, but it has to answer 1, 2, 3, 4, 5, and so forth. All right. So this is a very complex task, and yet you can use the same kind of mechanism. You can use a neural network, and you can use the stochastic gradient descent to actually learn to answer these kinds of visual questions. And the way that you do it is that you decompose the input. So what the input image is given some convolutional neural network, like the one I showed you before, and this creates an embedding. So this creates a number of real valued numbers, and you do the same with the text. Okay, typically with some recurrent neural network, for example, you get an embedding for every word. You sum that up, and then you have an embedding for the entire sentence. And this you feed into a fully connected neural network, and then you predict which of the answers is the right one. Okay, that's the architecture. And then by training, so by giving it thousands and millions of examples, these weights will actually become more meaningful, and we'll be able to predict meaningful answers. Okay, I was going to show a bit of, well, so this is just something, if you're interested, there's this website called playground.tensorflow.org. And what's nice about it is that you can play with the activation function and with the number of hidden layers, and it visualizes what each of the neurons learns and how well this is able to capture the task. So I think I will be in time trouble if I go into this. So just if you're interested, this is something fun to look at. You can even do it during the practical later. Okay, principle 2b. If you look too hard at the data set, you'll find things that don't generalize to unseen data. And this is a very important difference with traditional constraint optimization. In constraint optimization, you're trying to solve the problem, right? You're trying to find the optimal route. You want to minimize the total distance that all your vehicles are driving, okay? And the more you optimize, if you can prove the optimal, you're off best. But in machine learning, this is not the goal. The goal is not to do best on the training set. The goal is to do very well on an unseen test set. And an unseen test set sampled from the same distribution means that you need to generalize. Okay, that's this principle of generalizing. And why don't we sometimes generalize? Why sometimes doesn't this happen? And that we call overfitting. So let's have another look at why this happens. So I already showed you this slide. Let's look at a toy example. This is an old example from a book. And let's say that we want to discriminate two types of images of fish based on a camera image, namely salmon and sea bass. Nowadays, we would just run a deep network on this and it would do fairly well. But in the old days, and for the interest of explaining you what overfitting is, we're going to use an old school approach, meaning that we're going to pre-process the data. For example, we're going to extract the contours of each fish, as well as, and use that to measure the length of the fish, as well as the lightness, so how well it reflects the light from the lamp of the camera. And based on that input, it has to say, is it a salmon or is it a sea bass? All right. Now, with those two features and the training data that we have, it would look like this. Okay, so all of the black dots are salmons and all of the red dots are sea bass. Now, if we would learn a very simple linear function, so a weighted combination of the two features, then this would be an example classifier. So everything to the left of this line would be classified as a salmon and everything to the right as a sea bass. Now you can see that it misclassifies a few cases here and here. So this might be a too simple function, all right? It might be possible to do better. This is another function, and this is typically what happens when we would overfit. So in this case, we're learning a very complex function. So we're capturing all of the small little details of the distribution of the input data, but we can expect that it could be that this was a wrongly labeled data, or this was like the one odd fish, you know, and if you learn this kind of model and you apply this on unseen data, you're likely to have much more errors than you have with this simple linear function. Okay, but there's actually a middle ground possible, which would be this one, which is more like a curved line that trades off what is the likely space of CBOS versus Solomons. Okay. Now, how do we know whether a model is overfitting or not? Well, if you only look at the training data, you can't find out. If you would throw some multi-layer neural network on this problem using just those two features, what you would see is that over time, if you plot the train error on the error on the training set, you will see that the network says, I'm doing better, I'm doing better, I'm doing better, I'm doing better. But if you would then evaluate it on a holdout set, so a set that is not given to the machine learning method, you would observe that on this holdout set, accuracy is actually becoming worse and worse and worse because your method is overfitting. And so the sweet spot, it's a different visualization of the same curve. The sweet spot is really somewhere here, where on the training data, it's actually, so this is in terms of decision trees. So where the right numbers of nodes to use in your decision tree are those where your performance on the training data is most similar to your performance on the test data. And so the main message here is that overfitting will happen, especially if you use neural networks. And one method to overcome this is to have holdout data, so a validation set where you can check whether you're overfitting or not, and where you can do early stopping, for example. And so you can check how easy is it to overfit data. You can also check that on the TensorFlow playground. Okay, the third principle is that data science needs to be evaluated in the context of operation. And I already said a little bit about it because this one is I think, important, but also underestimated. And so in supervised modeling, we have data, we build a model, and then we apply this model on new data, and we do the prediction. So one of the most common pitfalls in data mining is that the training data is actually not consistent with the data of how it is actually used. All right, I've shown you the images of the CBOS versus the Salmon, right? Let's say that for this data science perspective, we used images of one facility, okay? And this one facility, one fish sorting center, because we're in the fish sorting business nowadays, takes those images and you build a learning model on it, okay? And now you wanna deploy this machine learning method to all of your fish sorting centers all over the world. Why is this problematic? This could be problematic because one of the features that we use is the light intensity. But the light intensity depends very much on the setup, on the type of camera that you're using, on the type of lighting that you're using, and on the angle at which you're looking at the fish. So if you're going to use this model on a fish sorting facility that has completely different lighting, it will very likely be that your system completely fails. And that's because the training data was only for this one facility and you're deploying it in another use. Other reasons could be that the samples that you have are bad. And so that means that somebody was very lazy when he didn't feel like labeling fishes. So he did it very badly. Or the features that you have are not representative for the problem. Now there's another pitfall, a dangerous pitfall, and that's that of survivorship issues. Let's say that we want to use machine learning in the financial domain, and we have a lending agency, and he wants to use machine learning to screen people that apply for a loan on whether to accept or reject that customer. Now, of course, this bank or this lending agency has been doing this for years. So it has all sorts of data on customers that it accepted or that it rejected, all right? So let's say that we're now using the data of the accepted loans. So we have the accepted loans, and then we look at the outcome of that loan. Did this client pay back the loan or not? Okay. Now, if we train the model using the accepted loans and what the outcome was, and we use this model to predict whether a new loan is going to be paid back or not, you are very likely going to be in trouble. And that is because the data that you have is only, or that you used, is only on the accepted loans, right? So you didn't consider the loans that were rejected. And if you would do that, your instances may be from a different distribution and so forth. I have a question, and I'm going to ask you to answer in chat. All right, and that's, what number is this? So please type in chat. It might be an odd question, but what number is this? All right, I see the answers are coming in. Ah, I was waiting for somebody like Jeremy Labroquer, all right? So, and Marianne de Freze, all right? So many of you, okay, Natalie, that's funny. So many of you think from a computer science perspective or even from a machine learning perspective, and you're trying to recognize a number in this image. But this is actually not a number, it's a heart, right? We all know that. If I ask you, what is this? You would answer a heart. But I asked you, what number is this? And so many of you felt forced to answer a number, but it is not a number, okay? And this is actually a major pitfall of many of our machine learning systems today. So I'm not going to do it live, but you can do it live on this website. This is a web-based demo of an MNIST digit recognizer. And if you draw a heart, because you can draw any number that you like, if you draw a heart and you press classify, in this case, it says it's a 0, and I'm 97% sure that it's a 0. All right. So this machine learning system is 97% sure that the heart is a 0. And the reason is that it only knows numbers, okay? It has never seen samples from a distribution outside of the numbers. And it also doesn't have a label, an output through which it can say, this is something else. Okay, so these are two major pitfalls that are actually limitations of AI systems today. But that's a bit too much maybe for this lecture. But so the distribution here is different and the output doesn't match. For those that are interested, can we do something about this? Actually, I'm also working on this topic. We have a paper very recently at DSAA 20 about probability of default estimation. So actually within the financial domain, where we add a reject option to the classifier. And so the main point here is, if you look, the first most important image is the top left image. Okay, so here what you see is that the red is what the classifier predicts as false, and the green is what the classifier predicts as true. And for any given input, so for any possible instance, even outside of the distribution that we learned from, it will either classify this is true or this is false. While on the other hand, the goal here, and that's what you see in the top left corner, is that we first, in this case, use density estimation. We first estimate, is an instance actually from the distribution that we trained on? And only if it is, should we predict a yes or a no. And if it's not from the distribution, it should reject. So the classifier should say, I don't know, I don't feel confident to answer this problem because I've never seen this before. All right, so this is a very recent, a very hot topic. So people are working on this, but I just wanted to give you that the idea of the pitfall here, and the distribution. All right, principle 4. Entities that are similar on some attributes are often similar on unseen attributes. And this is a concept that is used in most methods used in machine learning. An obvious case being in clustering. And let's say that we're given a handful of M&Ms, and you're asked, okay, how can we group these M&Ms into different clusters? And you might have the following cluster in your mind, so where you group them by color. And why are these in these clusters? Because they are similar, and their similarity is in this case based on color. And you could also actually cluster them based on whether the M is visible or the M is not visible. That would be another dimension on which you could cluster these things. Now, clustering is a problem that's very well studied, and it's also solved using optimization, mostly continuous optimization. Namely, you want to minimize the distance towards a certain cluster center over the feature representation. So the key concept here is that of a distance between objects. And this distance, there actually exists many distance functions, and the typical one being Euclidean distance, but you also have Manhattan distance, added distance for strings, and if you have more complex data like sequences, there's distance functions like dynamic time warping. You can even compare distributions using Cahill divergence and so forth. So as a small example here, let's say you want to group handwritten letters together, right? So you're given images of handwritten letters, and you want to group them into different groups. So that means that we have to work on the raw pixels. But an issue with raw pixels, let's say that we have 28 by 28 pixels. This is like a 700 plus dimensional vector. The thing is that if you take the handwritten letter and you shift it just a little bit to the left or a little bit to the top, or you stretch it a little bit, it doesn't change the number that is written, but it does change the pixels, right? So learning literally on these pixels is a very challenging issue. And so we know that convolutional neural networks are shift and scale invariant. So the good idea would be to use neural networks, convolutional networks, to learn a distance function. And this is something that's actually done. So this is an example. It also has a very nice online demo if you want to look at it. So the first thing it's doing is it's learning a neural network that, given the input pixels, is required so it has a hidden layer of a fixed capacity. And so the input is like 700 plus dimension. And the hidden layer is, let's say, 15 or something, right? And then based on those 15, there's another layer, which is the output layer, which again goes to the full 700 plus features. And this network should do autoencoding. That means that it's asked to predict what it is given as input, but it can't literally because the capacity of the hidden layer is smaller, okay? So it has to learn a hidden representation using just 15 real valued numbers, and with those real valued numbers, it should then learn, so that's the encoder part of the network, it should then learn a decoder part of the network that reproduces the input image as good as possible. And so this is called autoencoding. It's a very powerful and widely used technique. And if you do this, you actually get now a feature vector of 15 real valued values. And on those 15 real valued values, you can then use any standard clustering algorithm, because this fits in the traditional tabular format. It's just, every instance becomes 15 real value, right? And so you can actually cluster these, and we call that an embedding. We can cluster these embeddings, and that's one way to do this. Okay, and this is actually a 2D visualization, but you see that, for example, it clustered the zeros very well. Let me stress again that this method does not know the true label of each of these numbers. It would be easy if you know the true label. It was not given this information. Purely based on the pixels, it grouped these images together. And so it's grouping the zeros very nicely apart, but you can also see that 3s and 5 are more difficult to discriminate, as are 1s and very narrow 8s and so forth. All right, principle 5, I'm nearing the end of the principles here, is that to draw causal conclusions, you have to pay very close attention to the presence of unseen confounding factors. What does this mean? Well, if a method is able to classify something, for example, to say that it's a fish or not a fish, it's very tempting for us to look at to try to understand what is the classifier doing. For example, if this is a linear function, to look at the weights of this linear function and to conclude that, if the light reflection is very high, then it's more likely to be this type of fish, okay? But what we do here is we're drawing a causal conclusion, but actually the machine learning method that we used is not trained to do causal conclusion. It exploits correlation, all right? So machine learning models, they look at the input and the output, and they see what correlates between the input and the output. And in many cases, correlation implies causation, but as you've seen very often, it does not, correlation is not always, and there are many counterexamples, the same as causation, okay? So the real cause might be an unknown factor or might be just the way that you sampled the data and so forth, right? So it's very tempting to inspect a model and to see what causes things to be true or false. But let me give you this example. And again, I invite you to answer in the chat. And let's say that I've learned this linear regression function. Which of these features has the most impact? Please do answer in chat what you think is the answer. P-value. Well, if you know the answer to how to compute the p-value, tell me. Shapely values are the current hottest approach, but let's just take this question. What do you think? What feature has most impact? Okay, I see many of you already know that it's a trick question. All right, very good remark from Marianne. Depends on whether the feature have been normalized or not. That's a first thing. So it could be normalization means that you're reducing each of your input features to, for example, to have a mean of 0 and a variance of 1, for example. Okay, if this is not the case, and that's the remark that she made in chat, it could be that x1, x2, x4, x5 all have values in the range of 10, right? But that x3 has a value in the range of 0.1. Okay, so well, let me first of all say that indeed the natural reflex is to look at the instance with the largest weight, x3, and assume that that's the most important. But this is false. This is not true because, as Marianne said, if the features are not normalized, it could just be that x3 is a tiny value. And so the method needs to assign a high weight to it just to make it impact the decision. That's one reason why you cannot just look at the largest weight. The other reason is if you look at this equation better, then you'll see that x3 has a positive weight of 300 and x5 has a negative weight that's almost the same, namely 299, right? So that means that x3 and x5 are in effect canceling each other out. In fact, I can make the weight of x3 3,000 or 30,000 and the weight of x5 29,999,000, right? And they will still cancel each other out. So here in this case, it could be that x3 and x5 are confounding factors. So they themselves are correlated. And so inversely in this case, and so assigning them cancels out in this equation. And that means that it's most likely x4, which is correctly answered by a number of you. Well done. That should they be normalized, that x4 would be the best answer here. So I'm just giving this example to let you know that simply looking at the coefficients of a linear regression is not a good idea, and you should not be tempted to do that. There are more advanced techniques. Very popular is to use random forests as a classifier, and then within random forests there is a principled statistical way of coming up with feature importances. And so that's one thing. I think Daniel Vigo also mentioned it, that they're doing that within the VRP setting. But even in that case, you have to be careful with drawing causal conclusions. You actually shouldn't draw causal conclusions. And so based on an answer in the chat, I also mentioned shapely values. So if you want to explain not the entire model, the importance of the features in the entire model, but individual predictions, then there's something called SHAP, shapely values, that are a very hot thing nowadays in machine learning. All right. So these are the principles I wanted to share. Yeah, so the first one is that data science is always a process, meaning that you have to go back to the original problem and evaluate whether you solve that and not just stay at the machine learning level. The second is that it's actually optimization. The third one, the importance of generalizing to unseen data. The fourth one, make sure that your data matches all operational context. The importance of similarity and the fact that machine learning uses correlation and not causation. So I will open questions. I will start answering questions very soon. I just want to give one more slide, a very hands-on type of thing. So you're doing your PhD and you need to analyze some data. What should you use? Here are my personal recommendations. Many people will have many different recommendations. My personal recommendations: if you have to do an exploratory analysis of highly dimensional data, tabular data, look at Tableau. It's a web-only system, but it does this really, really well. If you have tabular data and you need to do classification or regression, the scikit-learn Python framework is highly recommended. If you need to do nonlinear regression on very large tables, XGBoost would be the recommended package. And if you need to do deep learning on sensory data, I personally recommend PyTorch. But as I said, there's many, many other frameworks. This is just, if you're just starting and you don't really know where to start, consider these ones. Yeah, it should be XGBoost. I think that's a typo. Okay. Okay, that's my old webpage, but I will put the slides on there, and the slides will also appear on the site of the school, of course. So I'd like to use the next 5 minutes to answer questions about this part. So please type questions that you might have, or just thoughts in the Q&A part of the chat.
You already have a question in the Q&A.
Could we classify other regrouping, anything that isn't fitting to one of our classes, and run an unsupervised ML on this other class? Okay, so you're talking about the out of distribution detection. The answer is no. So if you have training data and you're just going to add an extra label that says, I don't know this instance, then actually, right, and run an unsupervised ML on this other class. Yeah, so that's actually an approach, a common approach, right? So you first use unsupervised ML. You cannot run it on the other class because you haven't seen anything from the other class. So you're going to run an unsupervised ML on all of your instances that you've seen, namely a probability density estimation. So you're going to estimate the probability that it belongs to this distribution. And then the inverse of that you can use as the additional class. There are more advanced techniques like background check that will actually weigh the probability based on the background distribution with those of your foreground distribution. The next question is too abstract for me. How about using Koopman operators? I'm not familiar with Koopman operators, so if you could extend a bit in chat on what it is, then I might be able to answer. Do you have books, recommendation, or tutorial to learn how to create a good neural network? A good neural network being what are the number of layers, what are the number of neurons per layer, what are appropriate loss functions? This is a good question, Cyril. So determining the architecture, no, you should have left. I haven't answered it yet. I'm still answering it. Determining the number of layers and the number of neurons, that's actually the architecture of the neural network. And this is something which requires getting some touch with, and also lots of empirical evaluation. So it's best to use a standard deep learning book and to look at the type of architectures that people typically use and why they use them. And based on that, you can create a space of meaningful architectures. Actually, machine learning is constraint optimization as well, but it's a highly empirical research field, meaning that what you typically do is you do hyperparameter optimization. So for example, you determine the architecture in terms of the number of layers, but you don't fix the number of nodes at each layer. And then you search, okay, what if I train a network with, let's say, 5 hidden nodes? What if I train a network with 10 hidden nodes, with 20 and so forth? So you try each of these different hyperparameters, and then on a holdout set, so on a validation set, you check which of the networks was best, and you use that one. But this is described in standard deep learning network books, and there's also a good online book that I will ask to be put on the website as well, and I will add it in the slides too. All right. Is there any interaction between reinforcement learning and optimization? Very good question. Yes. So reinforcement learning, I haven't talked about it. It's about what happens is, the difference is that you're not just learning a distribution, but you're learning to make an action, and you get a certain reward for this action, right? And this is actually an iterative optimization process. So I would very much recommend papers at machine learning conferences, like using reinforcement learning to solve TSPs, to learn to solve TSPs, to learn heuristics for TSPs, or to learn to solve vehicle routing problems. There, you really see the interaction between two. The thing is that the reinforcement learning is learning a heuristic to find a single solution, and in optimization, we typically do a more systematic exploration, but there's many possibilities of something in the middle of the two. Could we have the slides? Absolutely. A question about causality. Deep learning explainability. There's a tutorial on, well, just search for a tutorial explainable machine learning. There's one of Guidotti, that's a name that you could look at. And there's others as well. If you look at some of the recent conferences, like ICML, ECML, and NeurIPS, there's probably tutorials on explainability in AI that you can check there. You can also ask me on Discord for more precise resources. Do you think that we use constraint optimization for architecture search, where we see the layers and so on as variables? No, so that's a question from Asim. I don't have an answer to that. No, so constraint optimization is mostly about finding the optimal solution, while in architecture search, if you're going to have, so there's a lot of work on AutoML, it's called. AutoML, automating architecture search. So how can we do this architecture search more smartly? Well, we don't have to evaluate each architecture. We don't have to train it fully, and we don't have to evaluate it fully. If we just train it a bit and we evaluate it on a part of the data, we can already get an estimate of whether this is a good architecture or not. And so, and based on that, you can then look at, so it's more like a kind of a star search, but with a changing your thing. So I wouldn't use constraint programming for that. So AutoML is the keyword here. If you have access for daily energy production for 1 year, can we effectively predict? Yes, Zineb, you will be very happy with the talk I'm giving this afternoon, because that's exactly what I'm working on. So I'm not answering this question now. I will in the afternoon session. How could we escape local optima during gradient descent? Interesting question, Samuel. You're clearly an optimizer. So if your loss function is convex and your network is convex, you will not get it into a local optima, but this is only the case if you have a simple linear, like linear regression, right? In all other cases, the network itself has non-convexities, and so you can get into a local optima. But in machine learning, the problem is not local optima. The problem is overfitting, all right? So you can handle both at the same time by training multiple variations, so in your hyperparameter optimization, and then choosing the best one in a subsequent step. Okay, this is the last question that I'm taking of Daniel. It's also luckily the last one. What is the best division sampling to use for the learning process? Does it change according to systems? It is not clear in division sampling. I don't get it. You mean whether we use 80% of the whole training data, whether we use 80% for training and 20% for testing, or whether we use 70% for training and 30% for testing? Yes, it's a very good question. Nobody can give you the answer. What you need to know is that, as I said, it's all about generalization. So if you're going to train on 50%, so ideally, the larger your training set and the larger your validation set, the better, right? But we have a finite number of things, so we have to make the choice. So the first question you need to ask is, if I train, what's the least amount of data I can train on so that what I learn is still meaningful? So you're not going to train on 5% of the data, right? But do you have enough data that you could learn on 50% or not? It depends on the application. It's also a bit empirical. On the other hand, if you only evaluate on 5% of the data, are those samples representative enough to give you a good estimate of how you're going to do on unseen data, right? So that's the problem. All right, and you answer yourself 70, 30, 30. That doesn't add up to 100, but it's true that we often use 70, 30, and then the 70 we again divide in 70, 30. This is something that's done in practice. Yeah. Okay, so I have to stop answering questions as I have more material that I wish to show you, but we can do a Q&A later, and I'll also be in the Discord. All right, let me first end this set of slides and open the other one. Okay. All right. So I'm now going to talk about actually hybridizations between constraint solving and machine learning. Namely, what if we want to learn from the user? And this is joint work with these three fantastic researchers in my lab at VUB. Obviously, you know what constraint optimization is. So it's about solving constraint optimization problems, routing, scheduling, configuration, and so forth. Now, as you've probably seen on Monday, the typical practice in coming up with a constraint model is that we first model the problem in terms of an exact, precise specification of constraints. And then we give this specification, this formal specification, to an optimizer, to a constraint solving system like a MiniCP. Okay, now let's ask the question, where does this model come from? All right, and actually you made the model, right? You're the optimization expert. But how did you come up with the constraints, and how did you come up with the objective function? And the answer is that that there is some domain specific problem, and there's a business understanding that it's needed, just like in machine learning. And in order to get that business understanding and to understand what the objective function is and what the constraints are, this typically involves many, many communications iterations with domain experts, and they in turn are in contact with stakeholders, different kinds of stakeholders, and so forth, right? And so the goal, actually, if you look at the whole process, then the goal is to create a model that captures all of these preferences as good as possible, so that the optimization, the solution that you get from the solver, also matches the goals of these domain experts and stakeholders. All right. Now, I would argue that the current process is too rigid and too static. And even if you don't believe me, let's just, for the sake of science, ask the question, can we make it less rigid and less static? All right. And actually, a lot of the works, and how can we make it less rigid and less static? And it's implicit here, by using machine learning. All right. And there's a lot of works that are working at this intersection and that are looking at the question, okay, can we learn part of this process instead? And I would group them into three categories, and you have talks about all three in this summer school, which is fantastic. So a first question, and the first amount of research that people look at is, can we learn the constraints, right? Instead of specifying what the hard constraints are, can we automatically extract from data what these constraints are? And As you know, Thomas Schick, so the talks of yesterday afternoon, dealt exactly with this. How can you learn these constraints? And there's hardening to get the constraints and so forth. A second body of research is not about learning the constraints. It assumes that the constraints are given and is then asking the question, can we learn the objective function? Right, so can we learn what the preferred optimal solution is? This is what I will talk about in this section and actually in the other ones as well. And then a third body of research, I want you to be able to discriminate the three, right? Although that there's some overlap. The third body of research is about learning to predict the solution. So can we use our network to either immediately predict the solution or to give such good predictions that you can use it as a heuristic to guide the search? And Daniel Vigo yesterday was actually talking about this type of learning, right? So I will talk about this type of learning. And so why this type of learning? Why am I working on this topic? And that's because I believe that knowledge consists of two parts of knowledge, and this is supported by social science research, and that is that in one part we have explicit knowledge, and explicit knowledge is knowledge that you can formulate in a formal language, right? So it's knowledge that is easy to write down. But apart from this explicit knowledge, there is also implicit knowledge. And this implicit knowledge in social sciences is called tacit knowledge. This is something that is very difficult to write down. And this implicit knowledge typically requires many iterations between the users. For example, who likes to work together and who doesn't like to work together? Okay, this is something that human planners take into account. All right, but it's typically not formulated into constraints, either because it's too confronting, or because you simply the optimization experts simply didn't get to the point where he realized that the way that who works with whom is an important factor. All right. So based on this implicit and explicit knowledge, many of our approaches are about this, namely, what type of implicit knowledge is there and can we learn this knowledge from data? So in this morning session, I will talk about learning one type of tacit knowledge, namely user preferences and social conventions, such as the example I just gave. And in the afternoon session, I will also talk about learning from a complex environment and learning from perception data, from image data, for example, or text data. Okay, so tacit knowledge, user preferences, and what I'm going to talk to you now about is mostly based on a paper that we published at CP last year, which got the Best Student Paper Award, the fantastic work of Rox, called Vehicle Routing by Learning from Historical Solutions. And it contains the word vehicle routing, so let me show you again this slide. And so Daniel talked about vehicle routing, but from the perspective of number 3, I will talk about vehicle routing from the perspective of number 2. All right. So what is the goal here? Well, if we look at this at how the constraint model comes into play, that's one thing. Let's now look at how a constraint model is used. So in this case, the optimization expert is long gone. He's sitting at home in his couch with his fancy car. But we do have the route planner, the person that's on the floor, and that needs to compute the routes for the drivers to drive out to. So this route planner fills in, okay, these are the clients, these are the number of vehicles, the typical parameters, and then it calls a route optimization software. Now what happens in surprisingly many cases is that the output of this optimization software, so the routing that is produced, is actually changed manually. So the domain expert looks at this and says, no. And he said, let's put this one with this car. And for example, instead of taking the tour this way, that driving in these neighborhoods in the morning is not very recommended. So I'm just going to swap the tour, and the cost is the same, but this one is much more preferred by the driver. For example, because of where the lunch break will be. Or it might shift one route to another route because this driver maybe is less experienced, And there's many, many more of these examples where there are some aspects which are not in the data, not in the constraints, and which are very difficult to capture. For example, who works well together, as I said before, but also that, and this is work with a real company, and they say, if possible, we'd like all the vehicles to end at about the same time, so that they're in the depot at about the same time, because then they can have a coffee together. But if this takes like 20, 30, 50 kilometers more, you shouldn't do this. But if it's possible, just by swapping one stop to another so that it becomes more balanced, then this should be done, right? And there's many other of these subtle changes. And these are, for example, CNG vehicles. So also, when do you fuel up and where do you fuel up? It's better to do it at the end of the route because it keeps the drivers awake. But if it takes more kilometers, you shouldn't, right? And so also robustness and so forth. So they make all of these manual changes. And then only that is sent to the drivers, who then give feedback to the planners, who then may make more manual changes in the future. So from this Macri point of view, the question that we ask is, can we actually learn from the changes that are made by the user? Can we learn what the true preferred solution is? And so the solution that's deemed optimal according to the current objective function is clearly not optimal according to the user. So can we learn how to modify this objective function, how to get an objective function such that what is produced by the optimization software matches the preferences of the users better. Right, so requires fewer changes. So learning these preferences means that it will reduce manual effort, but another important motivation here is that in a company, processes change, people change. So over the years, the type of routes that are driven, and just simply because of the behavior of people on the route, the kind of vehicles that you have, or the company policy, do you deliver big packages or do you deliver many small packages? Based on all of that, things change. But our current optimization approaches cannot take that into account unless you bring in the optimization consultant again. And so another important question here is, can we, if we do this learning, does it also mean that we can adapt to these changes over time? Now, so as I said, this is on real company data, VRP, actually a vehicle route. Well, it's not a vehicle route, a supplier in Brussels. And the data that we have is small data. So we're talking here about 6 months of data, which is from an operational perspective a lot, because 6 months is half a year. But from a machine learning point of view, it's 26 weeks. And that means that it's 130 weekdays. So you have just 130 instances. What can we learn from this? Now, in this work, what we did is we took inspiration from the machine learning community, namely from the data mining community, where there's a whole topic called mobility mining, and where people have been looking at GPS traces of an individual vehicle. The taxis, for example, or drivers, and because for insurance and so forth. And the question that's being asked in these machine learning papers is, given historical data of how people drive in a city, if we have a trace of one individual vehicle, can we predict where it is likely to go to? Or can we predict where it is likely to stop? All right, and so, the first paper is about driver turn prediction. So just if at the next crossroad, will it take a left, a right, or will it go straight? And so remainder of the route, origin, destination, and so forth. And most of these papers, what they use is they use Markov models, right? And so the question that we ask is, can we also use Markov models not to learn the preferences of an individual vehicle, but can we learn a Markov model to learn preferences across all of the vehicles in the vehicle routing problem, and then to solve the VRP on top of these preferences, right? And that's what this is about. And so can we optimize over them with constraint solving? So the key idea is that we have to somehow capture what the preferences of the user are in a probabilistic model. And if we can do this, then we can evaluate the likelihood of a routing. Okay, so we can evaluate the likelihood of a certain route as being the probability of observing this sequence of stops for each of the vehicles. What we're going to do is, if you would just consider a single vehicle, as in these mobility mining papers, then they treat the process as a Markov chain. And so you can say, okay, this is actually a chain of events. So it's actually a probability of a sequence. And based on that sequence, we can do some probabilistic approximations. So vehicle routing is not about a single sequence, but about a set of sequences. So for convenience to be able to use these methods, we first daisy chain all of the routes into one big route. And so if you go back to the depot and another vehicle leaves, we just chain them to each other, such that we get one long sequence. And then again, we can treat this as a Markov chain, as a sequence. And so the probability of the entire routing is the probability of taking the first stop times the probability of taking the second stop given the first, third stop given the second and the first, and so forth and so forth and so forth. All right, so this is standard probability of a sequence. And now we can take a first order Markov model approximation by taking the assumption that the choice that you're going to make next only depends on the state that you're in at the moment. So the probability of going to a certain client only depends on the client that you are currently at. All right, so this is a first order approximation. So it means that the probability of the sequence is the probability of being at the depot, which is evident, times the probability of going to the first stop, given that you're at the depot, going to the next stop, given that you're at the previous stop, and so forth and so forth. All right, now, this first order Markov model, this is a well-studied type of model. And we can actually estimate these probabilities, so the probabilities of the decomposition, by observing the transitions in the actual driven routes. Because we know in a historic solution whether somebody went from the depot to stop 1, or whether a vehicle went from the depot to stop 2. So we can count the frequency, how many times did somebody go from the depot to stop 1, and how many times did somebody go from the depot to stop 2. And we can do this for all pairwise stop combinations, all right? So the probability of taking a transition, so the probability of being at the depot and taking stop 1 will, we can estimate this by taking the relative number of observations in the data. So how many times did somebody take this given that he was at the depot? All right, and I'm not going into the mathematics, but this is of course all explained in our paper. So F is the frequency and N is the count. So how many times were you at this stop? Okay, so let's say let's say that we estimated these probabilities. What now? Well, what we now want to do is we want to find the maximum likelihood solution. So we want to solve a VRP, and we want to actually find a solution to the VRP that maximizes our probability. That means that it maximizes our distribution, which is the probability of the first stop chosen by the optimization times the probability of the second stop given the first, and so forth and so forth. All right, so we want to maximize product of probabilities. Now, what's very standard in probabilistic computation, and you've seen it yesterday as well, is that instead of working with products of probabilities, we take the log likelihood. So we take the log of this probability, and so the maximum of the product of these probabilities is the same as the maximum of the sum of the minus log probabilities. And there should be minus. All right, so if we do this transformation, then there's a very important observation to be made. That is that this looks very similar to the objective function of the standard VRP. In the standard VRP, you're maximizing, and it's written here, and you have, for example, distance between every two nodes, and you want to minimize the total distance driven, right, for each of the possible arcs that you can take in your routing. And now what the objective function becomes is that you want to minimize the minus log probability of taking this edge. And if you do this, you actually get the maximum probability. All right. So what's beautiful about this, I don't know what the next slide is. What's beautiful about this is that you can use any vehicle routing solver. All you have to do is estimate the probabilities and plug in the minus log probabilities as the costs, as the distances in this VRP solver. Okay, but we shouldn't stop there. All right. So we can do the probability counting by, we can do the probability estimation with counting, but is this the best thing to do? So let's go back to the business objective. Let's go back to the learning and see what it does and on what it does it. Well, if we do that, then we see that the training data is actually a sequence in itself. Namely, we optimized the routes 10 days ago. We optimized the routes 9 days ago. We optimized the routes 8 days ago. And even yesterday, we optimized the routes, right? So the training data in itself is a sequence. And that means that, well, this is a different point, but so it is a sequence that's one point. And the second point is that each of the routings that we computed in our company is different every day. All right, so the set of customers that we're seeing in a certain day will not be exactly the same as the set of customers of yesterday. As some will be the same and some will not be the same. So the routings composed are slightly different every day. And what I'm showing on the right here is actually a frequency plot. So there's a few clients which appear in almost every route. Then there's a bunch of clients that appear in many, and some clients that are, you know, kind of one-offs. And of course, it's the ones on the right that we can learn most from. But we have to take this into account, that the stops are always different. This is also, yeah. And then the second important one is that because these days are because it's every day, the preferences, so what the human planner has in his mind when making these changes can change over time. And in machine learning, we call this concept drift. And so there could be, in this case, what we saw in the data is that there was, at some point, there was a drop in the amount of clients being served and also a change in which clients are being served. All right, so can we take that into account as well? And the answer is yes. And so based on research in concept drift, instead of just counting the probabilities, what we can do is we can add a prior on each historic instance. So how important is the routing of yesterday given the clients that we need to serve today? How important is the routing of 4 days ago given the clients that we need to serve this today? And so this amounts to weighing each of the instances. You will have to check the paper to see how this fits in the equations. But there's 3 types of weighting schemes. Either we don't do weighting, so we give every historic day a uniform weight, or we give a weight by time, meaning that if we assume pure concept drift, then the most recent instance is the most important. And the one the day before is less important, less important, less important, and so forth, right? So you can have this decreasing weight scheme. But another aspect that's because client sets are different, you can also add a prior on how many of the clients that you need to serve today were in this historic instance and weight the historic instances based on that. All right, and so we ran some experiments. So here we're showing the different kind of weighting schemes. And this is centered around the concept drift. And so I showed you this figure in the top right before. So at some point, the number of clients changes. That's the point that's called 0 here in this figure. And so how well do the different weights behave? So as long as there's no concept drift, they behave kind of well. And so this is a domain-specific type of accuracy. But then when the change happens, what we see is that there's one of the weighting schemes called exp, which does better. And exp is actually an exponential smoothing over time. So it means that what seems to be doing best is if you take the historic instances, so the previous one most into account, and the next one exponentially less, and so forth and so forth. All right, so that's and even so, this is the data played off like this. So where there's a drop in the number of stops, which should be easier, but we also ran it in the inverse. And so let's say that there was a concept drift in the inverse direction, and then we also see, and this is a much harder problem, that the exponential smoothing is doing slightly better, especially immediately after the drop, obviously, but also in the end. All right, now a second really important point here is that from a machine learning point of view, this is where it stops, okay? We have concept drift. We know that we have concept drift. We have an evaluation measure, and the root difference and the arc difference. I didn't go into it, but we had to come up with these ourselves. So we have a way of evaluating accuracy, and by using this weighting scheme, we are actually able to get a better fit to predict the likely solutions best. But from a constraint optimization perspective, right? If we look at the domain problem, if we look at the optimizer point of view, then what we're doing is we're learning these preferences. But if we're learning the preferences, then what you're actually doing is we're mimicking the user choices, okay? That means that you can argue that what we're doing is we're copying the user, all right? Our system isn't specifically intelligence. Our system, it's just learning to copy the user. And so any mistake that the user makes will also be made by the system. Okay, so let's look at And so in optimization, what we typically do is you want to build a system that can be better than a user. And I don't mean this from a technological supremacy perspective, absolutely not at all. But the thing is that if we use optimization software, we can consider a larger number of candidate solutions. And also, given many constraints, these systems are better at resolving the type of conflicts that we have, right? So in optimization, we always want to see, okay, but can't we do better? Can't we find better solutions than that a person can with the limited time on that person's hand? Okay, so if we talk to these users, and as I said, we were lucky enough that we could do this, then the kind of explanations that they give is, well, actually, I prefer this other route, and I see it's 2 kilometers longer than the distance optimal route that you conclude, but I do prefer it, and it's only 2 kilometers more, right? So what these human planners do is they trade off the distance versus the preference, all right? So what we believe is the right approach here is not to purely learn the preferences and optimize the preferences, but rather to look at a sensible combination of the two, namely, we want to minimize distance, okay? That's the business objective. But in many cases, there are additional preferences that add on top of these distances, all right? And these should also be taken into account. So the right way to do, I believe, is to take a combination of the probabilities and the distances. And in the paper, we describe a principled way of normalizing the two so that you can do this without having to search too many hyperparameters. Right, but I think that this is the right approach from the domain perspective. Okay, so I'm nearing the. This is actually the last slide of the end of this part. So just a small recap. And so this was about tacit knowledge about learning user preferences, knowing what the constraints are, what the hard constraints are. And we had this likelihood trick where we could transform, where we could learn the probabilities and transform them such that we can use any existing VRP solver because the objective function is still a weighted sum over the edges. And then we saw that using this exponential smoothing, we're actually able to do much better than a purely distance-based and also better than the other schemes. All right. So with that, I will take, let's say, 4 minutes of questions, and then there's a practical that we prepared that I invite you to work on. So first, the questions. Is there a criteria, the number of hidden layers? Okay, so I answered this one. Is there a learning method of discrete function between data or numbers of n? That's also with respect to the previous talk. Is there a learning method of discrete function between data, which are numbers of n? Yes, so Jovial, this is a multi-class prediction. And so if we want to recognize the digits, handwritten digits, then it's either a 0 or a 1 or a 2 or a 3 or a 5 or up to a 9. Okay, so that's a multi-class classification. Next one. Does this work when the set of client is different every day? Very good question, Anonymous. So I'm going to show, I think you asked this question before I got to the slide. So let me just show you the slide again. And so that's why you have to start with the data analysis. If your set of clients is completely different every day, then the approach that we took is not going to work. You will have to somehow generalize over the clients. For example, you could group clients into geographical cells, and then you can look at probabilities of going from one cell to another. But in our case, what we saw is that there are regular clients, there are semi-regular clients, and then there are irregular clients. The irregular clients, we're not going to learn anything. And this is another reason why you should also add the distances if you're doing this type of hybrid method. It's these ones that we learn on. And the larger there are, the more that you can learn. Have you considered the time spent at every stop? No, in this work, we didn't. This is another way of using machine learning to learn part of the input model is if you would predict what the waiting time at every stop would be. And so you would use the predicted waiting time as the edge cost in this stop, and you would take that into account when doing the vehicle routing. This is a good idea, but that's not something that we that we looked at. It's also not a probability that you would learn, it's regression. All right, somebody's giving me a compliment. Thank you very much. Do you think it's scheduling problem and we use preferably to schedule the vehicles? We also consider time reasons as constraints. So could you use reinforcement learning for the problem that I described here? So, so in reinforcement learning, you need to define the reward function. And typically it should be easy to evaluate the reward. So the first question would be, what is the reward here? And I guess the reward could be the distance between the solution that you obtain and the actual solution by the user. So I guess you could use reinforcement learning problem. You could use reinforcement learning problem. It's a more advanced technique. I think we have to admit that. And so we decided to go for this, for a more supervised learning case, because we have the labels, we know what the true solution is, and so we can evaluate it that way. But reinforcement learning would be an interesting approach, and I would be very happy to read such a paper. About preference learning, do you envision to learn preferences per route planner, or will you stay at the high level preference learning? Yes, Lionel, this is a good remark. So it could be that that there are different routers and that they have different preferences. The mechanism that we presented would work on both. The thing is that if you're looking at the preferences of an individual planner, you typically have even less data. So then it could be interesting to see if you could learn, I'm just brainstorming, right? If you could first learn a preference model across all of the users, and if you could then like fine tune it to that specific planner, that would be interesting. Okay, I'm going to press the button. What is the best approach to optimize hyperparameters? Is grid search a good approach? Any low cost efficient methods? Misam, so this is a question from the previous part. Look at AutoML. All right, so for all practice, if this is not your research topic, if you just need to find good hyperparameters, use grid search, okay? If you want to know about more advanced approaches, racing and look at the topic of AutoML, Frank Hutter and so forth. But we don't personally use that because it just adds another layer of complexity. All right. Dennis, I should leave now. Thank you for the talks. Yeah, so you can ask questions on Discord during the day as well. We are actually a real approach for scheduling, but then it might be the other type of learning. Okay, very good. So so let me show you. So for the practical today, and so on the main page, you have given. There are links to each of the three practicals. And so the P0 one, that's the one that you should run to see if you've installed all of the necessary software on your system. So if you can run this one, then you're ready for the actual practical. And the actual practical is in P1. Actually, I still have it open, I think. Yes. So what are we going to do? Actually, in this practical, I'm inviting you to train your, well, I don't know if it's your first, but to train your own deep neural network to do handwritten digit recognition and to use that network to solve a visual Sudoku problem. All right, so visual Sudoku means that it's a Sudoku as you know it, except that the input is not the digits, but it's the images. And it's quite likely that Thomas talked about it yesterday. But so this is a different approach. And so how to do this practical, I advise you to sit together with a few of your fellow students on chat or on Discord or whatever, and walk through it, okay? So there's always an explanation, then you can look at the code, an explanation, look at the code, there's also comments. And so I explain two types of architectures and what they do and so forth. This is the stochastic gradient descent training loop, and you can use this to understand what it does. You can run each of the things, you can change things and so forth. Yeah, and by the time you get here, you will have trained a standard neural network using the hyperparameters that I gave, and you can now look at what the output is. And then the first real task for you is, okay, now just play around with the hyperparameters and see if you can train a better model. And then I show how evaluation is typically done. And if you then have a predictor, you can use it to solve a visual Sudoku. So we added a Sudoku here. This is code for sampling images. You can apply your predictor. And then, of course, you get predictions, but you still need to solve this Sudoku. And so to solve this Sudoku, I invite you to either use MiniCP, or if you like to stay in the Python world, use OR tools and model the Sudoku problem and make sure that it can operate on those predictions. Right, so then you have both separated, namely the neural network and the optimization. And in the practical of this afternoon, you will actually combine the two. So I invite you to play around and learn based on this notebook. And I will be in Discord, and a few of my PhD students will be on Discord as well if you have any questions. Thank you. So Christian, I don't know if you typically close the feed then, or?
Hello. So you already finished your lecture for this morning?
You're welcome.
All right. So thank you everybody for attending this morning session. So let's meet at PM for the...
Yeah, but so now it's the practical, right? So they still have 20 minutes to work on the practical.
Ah, sorry, I didn't get. I was sorry, I was occupied answering.
No problem. Yeah, but so now is the time to. And so I prepared this notebook. I just showed it. Now's the time to work with it and to learn from it. And so I will be in Discord for questions. But I think we can close the main session here.
Okay, perfect. So you can meet Tias on Discord for the practical session. And so, as I said, we meet again in Zoom at 2 p.m. Thank you very much. Bye-bye.